Welcome to our journey into the world of physics units. Before we dive into complex equations and fascinating phenomena, it's essential to understand the foundation of all physical measurements, units. Units give meaning to numbers in physics, allowing us to communicate and compare results accurately. Imagine trying to describe the length of a table without a standard unit. Confusion would be inevitable. In this video, we'll explore what units are, why they're crucial, and how they shape our understanding of the physical world. Let's begin by defining what a unit is and why it matters in every scientific measurement. Unit is a standard quantity used to specify measurements. For example, when we say something is 5 meters long, meter is the unit that tells us what kind of measurement we're dealing with. Units act as a common language in science, ensuring that everyone understands the scale and type of measurement being discussed. Without units, numbers would be meaningless and scientific progress would be impossible. In the next scene, we'll see how units help us compare and communicate results across the globe. Units are the backbone of scientific communication. Imagine two scientists measuring the same object, but one uses inches and the other uses centimeters. Without a clear understanding of units, the results would be confusing and potentially misleading. Units allow us to compare, replicate, and build upon each other's work. They also help prevent costly mistakes like the infamous Mars Climate Orbiter incident, where a unit mix-up led to the loss of a spacecraft. Clearly, units are more than just labels, they're essential for accuracy and consistency in science. Units come in many forms depending on what we want to measure. There are units for length, mass, time, temperature, and more. Each physical quantity has its own set of units tailored to describe it accurately. For example, we use meters for length, kilograms for mass, and seconds for time. These units help us quantify the world around us, making it possible to perform experiments, analyze data, and develop new technologies. Next, let's look at the difference between fundamental and derived units. Fundamental units, also known as base units, are the building blocks of all other units in physics. They represent the most basic physical quantities such as length, mass, and time. The International System of Units, or SI, defines 7 fundamental units: meter, kilogram, second, ampere, Kelvin, mole, and Candela. These units form the foundation for all measurements in science, ensuring consistency and clarity. In the next scene, we'll see how these fundamental units combine to create derived units. Derived units are created by combining fundamental units according to the rules of mathematics and physics. For example, speed is measured in meters per second, which combines the fundamental units of length and time. Other examples include newtons for force, joules for energy, and pascals for pressure. These derived units allow us to describe more complex physical phenomena, building on the foundation provided by fundamental units. Let's explore some common derived units and how they're constructed. International System of Units, abbreviated as SI, is the globally accepted standard for measurement in science. It provides a consistent framework for defining and using units, making international collaboration possible. The SI system includes 7 base units and a set of prefixes to represent multiples and submultiples. This system simplifies scientific communication and ensures that measurements are understood the same way everywhere. Next, we'll look at the 7 SI base units in detail. The SI system defines 7 base units: meter for length, kilogram for mass, second for time, ampere for electric current, Kelvin for temperature, mole for amount of substance, and Candela for luminous intensity. Each unit is precisely defined and maintained by international agreement. These base units are used to construct all other units in physics, providing a universal language for science. In the following scenes, we'll explore each base unit and its significance. Meter is the SI base unit for length. Originally defined as 1/10,000th of the distance from the equator to the North Pole, it is now defined by the distance light travels in a vacuum in 129979245 of a second. This precise definition ensures that the meter remains consistent and reliable, no matter where or when it's measured. The meter is used worldwide for scientific, engineering, and everyday measurement. Kilogram is the SI base unit for mass. For many years, it was defined by a physical object, a platinum iridium cylinder stored in France. Today, the kilogram is defined by the Planck constant, a fundamental constant of nature. This shift ensures that the kilogram is based on unchanging physical principles, making it more stable and universally accessible. The kilogram is essential for measuring everything from groceries to scientific samples. Second is the SI base unit for time. It is defined by the vibrations of cesium atoms in atomic clocks, specifically 9,192,631,770 cycles of radiation corresponding to the transition between two energy levels of the cesium-133 atom. This atomic definition allows for incredibly precise timekeeping, which is crucial for everything from GPS navigation to scientific experiment. The second forms the basis for all time measurements in physics. The ampere is the SI base unit for electric current. It is defined by the flow of exactly 1/1, 602,176,634 times 10^19 elementary charges per second. This precise definition ties the ampere to fundamental physical constants, ensuring consistency in electrical measurements. The ampere is vital for understanding and designing electrical circuits, powering devices, and studying electromagnetic phenomena. Kelvin is the SI base unit for temperature. It is defined by the fraction 127,316 of the thermodynamic temperature of the triple point of water. More recently, it's tied to the Boltzmann constant, providing a direct link to fundamental physics. The Kelvin scale starts at absolute zero, the coldest possible temperature, making it essential for scientific research and understanding thermal phenomena. Mole is the SI base unit for the amount of substance. It represents exactly 6,022,14076 times 10^23 elementary entities such as atoms or molecules. This number, known as Avogadro's number, allows scientists to count particles in a given sample, bridging the gap between the microscopic and macroscopic worlds. The mole is fundamental in chemistry and physics for quantifying reactions in substances. Candela is the SI base unit for luminous intensity, measuring the perceived power of light as seen by the human eye. It is defined by the light emitted in a particular direction by a source emitting monochromatic radiation at a specific frequency. The candela helps standardize lighting measurements, ensuring consistency in everything from laboratory experiments to everyday lighting design. SI units can be scaled up or down using prefixes like kilo, centi, and milli. These prefixes represent powers of 10, making it easy to express very large or very small quantities. For example, a kilometer is 1,000 meters, while a millimeter is 1,000th of a meter. Using prefixes keeps measurements manageable and avoids long strings of zeros. Let's look at some common SI prefixes and their meanings. Some of the most frequently used SI prefixes include kilo 1,000, mega 1,000,000, centi 1,100, and milli 1,1000. These prefixes help scientists and engineers express measurements efficiently, whether they're dealing with the vast distances in astronomy or the tiny scales of nanotechnology. By mastering SI prefixes, you can quickly interpret and convert between different units. While the SI system is the global standard, some non-SI units are still widely used in everyday life in certain fields. Examples include inches, feet, pounds, and gallons. These units can be converted to SI units using established conversion factors. Understanding both SI and non-SI units is important for interpreting data, especially when working with international teams or historical information. Converting between units is a fundamental skill in physics. Whether you're switching from centimeters to meters or from pounds to kilograms, the process involves multiplying or dividing by the appropriate conversion factor. Mastering unit conversions ensures that your calculations are accurate and your results are meaningful. In the next scene, we'll walk through a simple example of unit conversion. Say you have a length of 150 centimeters and want to convert it to meters. Since 1 meter equals 100 centimeters, you simply divide 150 by 100, giving you 1.5 meters. This straightforward process applies to all unit conversions. Just use the correct conversion factor and perform the necessary calculation. Practicing these conversions will make you more confident in handling measurement. Dimensional analysis is a powerful tool for checking the consistency of equations and conversions. By analyzing the units involved in a calculation, you can ensure that your results make sense. For example, if you're calculating speed, the units should simplify to meters per second. Dimensional analysis helps catch errors and reinforces your understanding of physical relationships. Maintaining unit consistency throughout calculations is crucial. Mixing units, such as using meters in one part of an equation and centimeters in another, can lead to incorrect results. Always convert all quantities to the same unit system before performing calculations. This practice ensures accuracy and prevents misunderstandings, especially in collaborative projects. Every physical quantity, such as length, mass, or time, is measured using a specific unit. The choice of unit depends on the context and the scale of the measurement. For example, astronomers use light years to measure vast distances, while chemists use nanometers for tiny particles. Understanding the relationship between physical quantities and their units is key to interpreting scientific data. Standardization ensures that units are defined and used the same way everywhere. International organizations, such as the International Bureau of Weights and Measures, oversee the definitions and maintenance of units. This global agreement allows scientists and engineers to collaborate effectively, share data, and build on each other's work without confusion. Units have evolved over time, from ancient systems based on body parts or local standards to the modern SI system. Early units varied widely between regions, making trade and scientific exchange difficult. The development of standardized units, such as the meter and kilogram, revolutionized science and industry, paving the way for global collaboration and technological progress. Accurate measurements are the foundation of scientific experiments, and units play a central role in this process. By using standardized units, scientists can replicate experiments, compare results, and draw reliable conclusions. Units also help communicate findings clearly, ensuring that others can understand and build upon the work. Units aren't just for scientists, they're part of our daily lives. We use units to measure distances when driving, weights when shopping, and time when scheduling appointments. Understanding units helps us make sense of the world, from cooking recipes to weather forecasts. Mastering the basics of units empowers you to navigate everyday challenges with confidence. Modern technology relies on precise measurements and standardized units. From building bridges to designing smartphones, engineers use units to ensure safety, efficiency, and performance. Advances in technology often depend on our ability to measure and control physical quantities accurately, highlighting the importance of units in innovation. International trade depends on standardized units to ensure fairness and transparency. Whether trading commodities, manufacturing goods, or shipping products, consistent units prevent misunderstandings and disputes. The adoption of SI units has streamlined global commerce, making it easier to do business across borders. Despite standardization, challenges with units still arise. Differences between SI and non-SI units, errors in conversion, and misunderstandings can lead to mistakes. Staying vigilant and double-checking units is essential, especially in high-stakes fields like engineering and medicine. Awareness of these challenges helps prevent costly errors. Each unit has a standard symbol, such as M for meter or kg for kilogram. Using correct symbols and notation is important for clarity and precision in scientific writing. These symbols are internationally recognized, making it easy to share and interpret data across languages and disciplines. When reporting measurements, it's important to use the correct number of significant figures and include the appropriate unit. Significant figures reflect the precision of a measurement, while units provide context. Together, they ensure that results are both accurate and meaningful. All measurements have some degree of uncertainty, which should be reported alongside the value and unit. Uncertainty reflects the limitations of measuring instruments and methods. Including uncertainty helps others assess the reliability of your results and compare them with other data. Scientific notation is often used to express very large or small numbers, especially in physics. When using scientific notation, always include the unit to provide context. For example, 3 × 10⁸ ms specifies the speed of light in meters per second. This practice ensures clarity and avoids confusion. When writing equations in physics, always include units for each quantity. This practice helps verify that the equation is dimensionally consistent and that the results make sense. Checking units is a simple but powerful way to catch mistakes and deepen your understanding of physical relationships. Different scientific fields sometimes use their own customary units. For example, astronomers use parsecs and light years, while chemists use liters and atmospheres. Understanding these units and how they relate to SI units is important for interdisciplinary work and interpreting research from various domains. In computer science, units are used to measure data storage and processing speed. Common units include bytes, kilobytes, megabytes, and gigahertz. While these units aren't part of the SI system, they follow similar principles and are essential for understanding technology and digital systems. Medical professionals use units to measure everything from blood pressure to medication dosages. Accurate use of units is critical for patient safety and effective treatment. Medical units often include milligrams, milliliters, and beats per minute, each tailored to specific measurements in healthcare. Engineers rely on precise units to design, build, and test structures, machines, and systems. Whether calculating load-bearing capacity or electrical resistance, using the correct units ensures safety and functionality. Engineering often involves converting between units and applying them in complex calculations. Environmental scientists use units to measure air quality, water purity, and energy consumption. Common units include parts per million, liters, and kilowatt-hours. Accurate measurements and units are essential for monitoring environmental changes and developing sustainable solutions. Astronomers use specialized units to measure vast distances and timescales. Light years, parsecs, and astronomical units help describe the immense scale of the universe. Understanding these units allows scientists to communicate discoveries and explore the cosmos effectively. Chemists use units like moles, liters, and grams to quantify substances and reactions. Accurate measurements are crucial for mixing solutions, analyzing compounds, and conducting experiments. Mastery of chemical units enables precise control over laboratory processes. Sports use units to measure performance, such as meters for distance, seconds for time, and kilograms for weight. These measurements help track progress, set records, and ensure fair competition. Understanding units in sports adds depth to our appreciation of athletic achievements. As science advances, our understanding and definitions of units continue to evolve. New discoveries may lead to even more precise definitions, ensuring that units remain relevant and accurate. Staying informed about changes in units helps scientists and students stay at the forefront of research and innovation. Summary: units are the foundation of all measurements in physics and beyond. They provide a common language for science, technology, and everyday life. By understanding and using units correctly, we ensure accuracy, consistency, and progress in every field. Whether you're a student, scientist, or simply curious about the world, mastering the concept of units is an essential step on your journey of discovery.